This conference will now be recorded.
So very good evening. We were studying atoms, atomic spectra, etc. We'll be learning today. So we had already learned Bohr's atomic model, and we have learned that Bohr's atomic model can provide the explanation for the line spectra. So what is line spectra? What is actually hydrogen spectra? What are hydrogen energy levels? How we get various spectral series, etc. We'll be learning today. So let us start with this energy level of hydrogen atom. So in the previous day we have calculated the radius of various orbits. We have according to, okay, good evening Deepa, you have also arrived, very nice. So we have seen according to
Good evening, sir.
yeah, we have started our class, you can just start listening. So today we'll be learning basically the energy level diagram, then spectral series of hydrogen atom, and excitation, ionization potential energies, etc. So excuse me. So we have learned according to Bohr's atomic model that nucleus situated at the center and electrons are revolving around various orbit. Okay, so in various orbits electrons are revolving around the nucleus, and we have seen that these orbits are named by quantum number n is equal to 1, 2, 3, 4, etc. And these are stationary states. That means when electrons are revolving around this particular orbits according to quantum condition, like what is quantum condition? L is equal to nh by 2 pi. This is the quantum condition of Bohr's postulates. According to this condition, we get this quantum number n is equal to 1, 2, 3. These are the stationary orbits. And we have also derived radius of various stationary orbits and the speed of the electrons in various stationary orbit, and also we have calculated the total energy of any orbit when electron is situated at any stationary states, or at any n is equal to, like, any quantum number n is equal to 1 or 2 or 3. We can calculate the total energy of the hydrogen atom by using this formula. This we had already derived in the previous day. We had already derived, this is the total energy. Okay, total energy of a hydrogen atom. Sometimes hydrogen atom is written as H atom also. And you look here, this n is the quantum number, or the number principal quantum number. This n is the principal quantum number. And see, this En means actually in general this is the total energy for any state you can calculate. For hydrogen atom, this is actually a general formula for energy in the hydrogen or hydrogen-like atom. I had stated that day what are hydrogen-like atoms. Like hydrogen has only one proton and one electron in the outer orbit. So any atom which has only one electron in the outer orbit, they are called hydrogen-like atom. Like see alpha particle 2He4. So they have, see, this is the Z2. But if you take hydrogen singly ionized atom, then you get Z is equal to, actually you get one electron in the outer orbit. Similarly, lithium, doubly ionized lithium and triply ionized beryllium, they are called actually hydrogen like atom. So we can calculate the total energy of any stationary states. So if I want to calculate E is equal to 1, then N is equal to 1. That means this is the lowest stationary states. And we have seen the energy was minus 13.6 electron volt. Okay. So look, this particular formula will tell you how you get various energy levels, or see the orbits, stationary orbits are actually having, like each orbit having a specified energy, a specific energy. So E1 denotes n is equal to 1 level has this much energy. Okay, minus 13.6, and with the minus sign, what is the significance of this minus sign? Minus sign in the total energy signifies actually bound state. Bound state, any system, any bound system. See, in this case, electron is not going to go away by its own accord. It will be always bound to the nucleus. That's why this system is called bound state, and bound state always have negative energy. Bound state always has negative energy. Okay, negative energy. So electrons are bound. That's why this energy is actually negative energy. And see, n is equal to 1 we have put. Similarly, we can put n is equal to 2, 3, 4, etc. So if we keep on putting n is equal to 1, 2, 3, 4, etc., then we get various energy levels or energy of various stationary states. So this is what is shown in this figure in the right hand side. You can look here. So when we put n is equal to 1, we get minus 13.6 electron volt. So this is the energy axis. And see, as you increase the n is equal to 2, this has energy. This n is equal to 2 level has energy minus 3.4. You can just 2 means minus 13.6 by 4. You divide with 4, you will get 3.4. Okay, minus 3.4 electron volt. Similarly, if you increase the quantum number, principal quantum number n is equal to 3, n is equal to 4, as you go away, like go along, like increasing ascending number of principal quantum number, you get various energy levels. So that's what we can see. So these are actually called, this is called energy level diagram. This is the one. So this is the one called energy level diagram of hydrogen atom. Okay, now look here, there are few things we need to learn. See, when n is equal to 1, n is equal to 1, that means it has energy minus 13.6 electron volt. If you put n is equal to 2, you get minus 3.4 electron volt. So among these two, which one is the least energy? This is the least energy. So this has least energy, and this least energy state is called ground state. Okay, least energy state is called ground state. Ground state. Ground state, why? Because here energy is the least. So any system in the physical world, they try to come to a state where its energy will be, total energy will be least. So that state of any system is called its ground state. So in this case, hydrogen will be at ground state when the electron is situated here, n is equal to 1. and that time it will be having the least energy, that is minus 13.6. So this is called ground state when we write n is equal to 1. Now if the electron, instead of staying at n is equal to 1 level, if it is there at n is equal to t level, now its energy is no longer minus 13.6. Now the energy will be E2, that is minus 3.4 electron volt. So now the electron has this much energy. So is the system still in the ground state? No, its energy has been increased. So when energy is increased of the system, of any system, then that system is called excited state. Excited, see, the system is excited. Okay, so then it is called excited. So the hydrogen atom is excited when the electron is situated any energy level other than this n is equal to 1 or the ground state. So when I say n is equal to 1 is the ground state, then n is equal to 2 is the excited state, and this excited state is called fast excited state. So n is equal to 2, this state is called fast excited state, because after ground state this is the fast state or the fast energy level. That's why it is called fast excited state. N is equal to 3, it's called second excited state. So these are various. Then again n is equal to 4 will be third excited states, etc. Now if so, but one thing you have to remember, that in general electron will try to be in the ground state, its normal thermal equilibrium state, or its ground state. It will try to be in the E1 level or having energy minus 13.6. But only when it will be given certain energy in terms of heat or whatever, then it will be having energy more than minus 13.6. If by chance the energy becomes exactly equal to the difference between this fast excited state and the ground state, then the electron can make a transition up to this level. Okay, so we have learned in Bohr's second postulate, third postulate, that is the frequency condition. We have seen that the electrons will not emit energy when they are revolving in various stationary states. But when they make a transition, suppose this is n is equal to f, and this is n is equal to some electron is there initially in the higher energy state or higher level. So you can see these are called higher energy levels. Okay, these are higher energy level. Now if the electron is at higher energy level initially, and then it comes back to lower energy level, the difference between this energy only will be emitted as photon. Okay, emitted as photon. So that's why we see discrete line. Okay, we see discrete line. Okay, so when an electron make a transition from this n is equal to 2 to n is equal to 1, the excess energy, how much the excess energy, see, we'll find out what is the difference between the energy level. So minus 3.4 minus of minus plus 13.6 electron volt. So what is the energy difference? You can see this will be 10.2 electron volt is the energy difference between these two. So when an electron is given at least this much energy, 10.2 electron volt, or maybe more than that, then only it will be making a transition to second level. So this is called excitation of electron. So when an electron is actually making a transition from a lowest energy state or any lower energy state, suppose electron can go from 2 to 3 also. So compared to 2, n is equal to 3 level and n is equal to 2 level, n is equal to 3 level has greater energy, that is minus 1.51. So when an electron make a transition from lower energy to higher energy state, then it is called excited. Okay, so the electron is excited, or the atom is at excited state. Okay, so this is called excited state. And see, one more thing is that, so these levels are actually, see, electrons after reaching to this higher energy level, they will not be able to stay for longer time, not longer than 10 to the power 8 second, or 10 to the power minus 10 second. Not longer than this much time it can stay in the higher energy level. So immediately it goes back to the lower energy state, or the ground state energy state, ground, yeah, so ground level. And then during making this transition, it will emit a photon of energy exactly equal to the difference between these energy levels. Okay, so this is how, so line spectra can be obtained. Now one more thing you can look from this energy level diagram, that when the quantum numbers are increasing, see the difference between the energy between two successive energy levels has decreased a lot. Look, this was 10.2 electron volt, this difference. Now this difference, how much it is? So it will be 9, and then this will be 6 to 8, and then 2, so 1.89 or 1.8, something like that. So see, gradually you can see gradually the difference between successive energy levels. Okay, energy difference between the successive levels are decreasing slowly. Now if you increase further and further this principal quantum number, you look what will happen. So see, energy level becomes continuous. See, no longer you will find any gap between two successive energy levels at very large distance from the atom. So this is the case. Suppose here it is, the electron is here, then it is actually no longer bound to this electron, because it will have, see, continuous energy level. No longer it will have discrete energy level. So this is called ionized state or free state, free electron. Here electron can be freely roaming here and there, because here in the free state energy levels are continuous energy level, energy continuous energy. So when an electron is actually taken to infinity, or just knocked out from an atom, then its energy will be zero. Okay, excuse me. So that will have energy 0, or it will have continuous, actually it can roam around anywhere freely. So that state is called ionized state, and you can see this energy levels are continuous. No longer you see any line, and there is an, yeah, actually there are lines, but they overlap on each other. So that's why there is no gap between successive energy levels, and that's how they creates a continuous band kind of that. Okay, so continuous kind of continuous band they make, and anywhere electron is situated, it will be able to make a motion. So if the electron is here, it can easily move it to here freely, anywhere it can move. So this is called ionized state. So at the ionized state, energy is taken to be, so E infinity, when the electron has been taken very far away from the nucleus. That means the tending to infinity. Radius tending to infinity. So in this case, the energy will be 0. You can just put it here. See, we have E n is equal to minus 13.6 by n square. So you put n is equal to infinity. So what you get? You get energy is equal to 0. So this is what is the hydrogen energy levels. Now this particular diagram is very easy to understand, and once we understand this diagram, then it will be very easy for us to know the spectral series, etc., and transition, etc. Now one more point I just want to make here. You look, see, when I just say one electron has to be excited from this energy level to this energy level, so immediately suppose it is excited from first excited state to second excited state, that means your energy difference is actually E3 minus E1, sorry, E2 minus E3. So this is the energy difference. So you have to find it out what is the energy difference, and that much energy if you are giving an electron situated at the excited state to a first excited state, it can make a transition to the second excited state. And as I said, electrons in the excited state cannot be forever. They will immediately actually come back to the ground state and leaving the excess energy as photon. Okay, so this is called emission of energy. Okay, we'll see this expression is very important expression for us to calculate various energies and etc. Now we'll see, as I have explained over here, and also from Bohr's frequency condition we have learned that when electron make a transition, that time only it will either accept or emit energy. Okay, so depending on what an atom is doing, like electron is doing, whether it is de-excited from higher energy level to lower energy level, or whether it is excited from certain energy level to higher energy level, depending on that there are two types of energy spectrum we can get. Two types of hydrogen spectra we get. One is called emission spectra, another one is called absorption spectra. See, through the rarefied gas, white gas, okay, if light of continuous energy, okay, energy is passed through then what happens from this light from these lights actually, or see this is okay. So when we do one thing, let us so do this thing, this small experiment, like you have cathode and anode, just like Thomson's experiment. You have a glass container which is evacuated, okay, evacuated and filled with certain gas, and see, when you apply certain electric potential across this tube, what happens, these atoms actually they absorb some energy from this accelerating potential. Actually how it does that, you have actually, if you have like more than one atom or two atoms, so what they have, they actually transfer energy through collision, okay, through collision. So by collision, higher energy or some atoms which are having higher kinetic energy, they will actually collide with the other one, and by that they will transfer energy from each other. So certain atoms which has electrons, they will actually, like electrons in the outer orbit, one or more than one, what they will do, they will absorb that energy, okay. By absorbing that energy, the electrons will be excited to higher energy level. As I said, they will be excited, okay. So upon excitation, when they de-excite, they will emit various kinds of frequencies, okay, various frequencies. So if you have certain gas, rarefied gas over here, and you are applying high potential across this tube, okay, now what will happen? This accelerating potential will excite the electrons in the atoms, gas atoms. So those electrons, when they de-excite, so suppose some electrons, this is initial state and this is the final state. Oh, sorry, I just take either way. Suppose this is the initial state, this is the final state. So this is the lower energy level. Here actually initial state is having higher energy level. So suppose electrons are excited to certain level here, they will de-excite to the lower energy level immediately, or the ground state immediately. So during that time they will emit energy. If the frequency, like photons, if the frequency of the photon is nu, then that photon will have energy h nu. So depending on nu, what is the, and nu depends on this gap also, principal quantum number, at which state it is going. So there are many possibilities, because there are many energy levels. So depending on which level it is getting excited and coming back to which level, depending on that, the energy, like, or depending on the energy gap between the excited level and de-excited level, or the lower and higher energy levels between which it is making a transition, the frequency will depend with that. Okay, that means, like, it depends on the principal quantum number from which one to which one it is going. So depending on various probabilities, you will get various frequencies. So you'll get various wavelength. That means you are getting various lines. Okay, and see, I'll show you here. If you get all the lines, actually this is called continuous spectrum, when you cannot separate various colors distinctly. Okay, but for a hydrogen atom, we have seen, for a hydrogen atom we see discrete lines, right? This is called emission spectra, when electrons are, see, as I said, in the evacuated glass tube, if you apply high potential, the electrons will be excited, and then when de-excited, they'll emit various frequencies, or various, like, lights of various radiations of various wavelength. And if they are in the visible region, we will be able to see this kind of lines. In fact, in case of hydrogen, there are various series of lines like this, and only the Balmer series is visible. So this is emission spectra when electrons are de-excited from excited state. Now look, I had see I have already shown you, this is the initial, the higher energy level, and this is the final, suppose the lower energy level. So now see, when the like, electron is in the lower energy level, to get excited to here, it needs the energy this much only. Okay, this much energy difference you needed. I mean to say, the energy it is releasing is the same by amount when it is getting excited to this level. So the energy difference between these two is always fixed. So that's why when an electron has to be excited, it has to absorb the same energy as it was releasing while de-excitation. Okay, that means if we see some frequency, some light of frequency nu, so the energy of that photon will be h nu. Now when you are exciting the atom, you have to provide this much energy only to this electron to go to the state. That means there are two ways. You can get absorption spectra, or you can get emission spectra. So emission spectra I have discussed. Now absorption spectra, if you have, suppose, the same tube and closed tube, you have certain gas, rarefied gas. Now what you are doing, you are not applying potential. What you are doing, you are just passing a light continuous, like which has all the frequencies from 0 to up to like visible range or maybe any range. You have all the frequencies in the light. Okay, if your light rays are passing through that, you will see, if you take a spectroscopy and analyze the light which is passing through the gas, you will see some lines are missing. Some lines are missing. See, some lines are missing, and those places you will see in the continuous background, you will see some black line. You see, this is the continuous background, continuous background, continuous background. Bright continuous background, and in the background you can see some black line at exactly at the position where we see emission lines also. Okay, so this is because the gas, like atoms, electrons of the gas has absorbed the energy having frequency or wavelength this much only. Okay, so this is called absorption spectra. So in the absorption spectra, what we do, we pass a light through a gas. Then the light which is passing through the gas, rarefied gas, we analyze that particular light using spectroscope. Okay, using spectroscope, then we get to see these black lines in the continuous background. In the emission spectra, what we do, we take a tube like this, we take a rarefied gas, and then we apply high electric potential such that electrons goes to excited state and then come back to ground state, and by that it will release energy. In absorption spectra, it was like electrons were absorbing. In emission spectra, electron will actually come from higher excited state to lower excited state, so that's how they will emit the energy. So emission spectra is actually, we will see these bright lines of various frequencies in the black background. You look, this is the black background, we will see exactly this figure if you go for doing experiment in the laboratory, then you will exactly see this kind of spectra. Absorption spectra, background is bright, and emission spectra, background is black. Okay, so this is what about hydrogen spectra and emission spectra and absorption spectra. Now what we'll learn little bit more about this spectra lines and related to their energies. See, we have already discussed this frequency condition. Now see, we have also learned that when electron make a transition from higher energy state to lower energy state, then it release the extra or the excess energy. So this is what is the condition. If the nu is the frequency of the emitted photon, then h nu is equal to the energy difference between these two particular level. Now, as I was taking in general a final state to initial state, okay, so the energy, see, you can see I had this energy equation, so I can find out what is the frequency emitted by writing n is equal to n2 minus en1. So n2 means this is the initial level, sorry, this is the, okay, let us write, this is n1, this is n2. Final to initial, in fact you can write final to initial, energy level difference. Okay, energy difference, so you get final to initial. Okay, so by doing that, look, we can actually find out various frequencies emitted during various transitions. Like transition can happen from, see, 2 to 1, 2 to 3, sorry, 2 to 1, 3 to 1, etc. So these are various probabilities. Even if we just consider further higher orbits, then n is equal to 4 to 1, 4 to 2, 4 to 3, okay, again 3 to 2, 3 to 1. So there are various probabilities. Okay, so we have many such discrete lines. Okay, now if you want to calculate what is the frequency of the light emitted when it comes from some final like initial state to final state, then you can use this is the equation of frequency. So 2 pi square, k is actually here 1 by 4 pi epsilon naught. This is the k. You can put it here, and z is the atomic number. For hydrogen it will be 1, and this is the quantum number. So you can see the energy or the frequency depends on the quantum number, and rest these are all constant, only depending on like which level to what it is going. Depending on that, this frequency you get, emitted frequency you get. Okay, now see nu nu, if you divide this with h, then you get nu. So this is what is written. Now again nu bar, this is called wave number. So wave number is actually defined as nu by c, that means 1 by lambda. Reciprocal of wavelength is called nu bar, or like this is denoted by nu bar. Reciprocal of wavelength is denoted by nu bar, and that is called wave number. Okay, so that is called wave number. See here 2 pi square m k square z square is e to the power 4 by c h cube. So this particular factor, actually if you put z is equal to 1, okay, then it is 2 pi square m k square e to the power 4 by c h cube. So this is called Rydberg constant. So this Rydberg constant has value 1.097 into 10 to the power 7 per meter, 73 per meter. Okay, per meter. So this is called Rydberg constant, and it will be given in your exam what is the value of Rydberg constant and all. And you look, we'll see various spectral series now. Spectral series. So what is spectral series? Actually, long back back when the quantum hypothesis was not given by Bohr. Okay, even then also Bohr had actually given, Balmer had given an empirical formula which we have just now learnt. This empirical formula to find out various frequencies of the spectral lines observed from hydrogen atom. So now we'll see when the electron in the hydrogen atom makes a transition from various level, and just by observing very carefully the hydrogen spectra. See, hydrogen spectra, the full hydrogen spectra is not shown here in this color, otherwise we would have been able to understand it bit more. So but anyway, we can understand from here also. This is the hydrogen spectra. So if you see, there are a set of frequencies or wavelength, or set of wavelength of the radiation we get from hydrogen atom. A set of wavelengths, they are very near to each other, and their changes are actually very regular. Like see, there are 5 lines, so 1 2 3 4 5 6 lines. They are actually in a particular manner they are arranged. Their frequencies and the difference between the frequencies, they are actually changing in a regular manner up to this. And again you see another series of colors or frequencies or lines they are arranged in a very regular manner. That means the difference, energy difference between each line, like successive lines, are almost similar in these 5 or 6 lines. Okay, 5 lines at least. Then another series of lines we see, they have a particular arrangement, particular relationship between them. So among them, so if we see the hydrogen spectrum, we see such 5 different series of lines which are actually nearly correlated to each other. Like, so these series are actually named as different scientists name because of their, after their inventors. And these series are Lyman series, Balmer series, Paschen series, Brackett, and Fan series. So you might be little bit surprised or maybe not understanding fully. So what I am trying to make you understand that if you have a hydrogen spectra, complete hydrogen spectra, you'll see some lines are here in a regular manner arranged, and some lines are like this, and some lines are having some other regular arrangement. So these lines are called series. These are called series of lines. Okay, series of lines. So these series of lines follow a particular pattern, particular law, or particular rule. We'll learn those things, and this particular series of lines will follow a particular law. This also will follow a particular law. So each series of lines or is actually collection of lines which are called series, will follow a particular law. So that's why these are called different spectral series of hydrogen atom. So now we'll see. So there are mainly, first is actually we'll write Lyman series. Then Balmer series. Balmer, Balmer, Balmer series. Then third is Paschen series. Then Brackett, fourth. And then fifth series is also there, that is Fan series. So Fan actually start with P Fan series. Okay, so these are various spectral series we see in case of hydrogen atom. Okay, nice. So we'll see, as we were discussing, that each series of lines, they will follow a particular law or rule. So see, for Balmer series we are doing now. Oh, sorry, Lyman series maybe. So Lyman series, what rule they follow? So for Lyman series, see, we can write this nu bar, or the reciprocal of this wavelength is Rydberg constant into 1 by, see, so this is 1 by 1 square minus 1 by 2 square. Okay, into, that means, see, first of all, let me write the general formula for this, then I'll write for Lyman series, then you will be able to appreciate. So we have already learned that nu bar is given by R, Rydberg constant, into 1 by nf square minus n initial square. Okay, this is what we have learned. Okay, now see, for Lyman series, what does this mean? Electron is making a transition from some initial state to final state. Okay, so like we have n is equal to 1, 2, 3, 4 various levels, right? I take this as n is equal to 1. So this is n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, n is equal to 7, 8, like that I am taking. N is equal to 7, n is equal to 8, etc. So these are principal quantum number. I can take one by one, like in the ascending order, and as we go higher and higher, energy increases compared to the lower energy level. And see, this will be actually having very less space, but my drawing is not according to that. But anyway, just to understand this Lyman series, I am drawing this. Okay, so look, the frequency or the wavelength you get 1 by 1 by lambda you get for Lyman series. So the wavelength you get in the Lyman series will be obtained by, the final state is 1 square divided by initial state. Anything you can take initial state for this case. So nf is 1 and n initial can be starting from 2, 3, 4, 5. This is actually emission spectra or de-excitation. So Lyman series, you will get the Lyman lines in the Lyman series if electron which is at n is equal to 2 makes a transition to n is equal to 1, or it make a transition from n is equal to 3 to 1, or n is equal to 4 to 1. So the final state is same for all the lines, only initial state changes. So that's why energy also will be changing. So see, this has greater difference in energy. Okay, so this is how you get various. So depending on this initial value from where the electron is de-exciting to ground state n is equal to 1, you will get various wavelength. So you will get various wavelengths. So these lines actually they follow the rule is that from anywhere starting from n is equal to 2, if they come to de-excited, they are actually de-excited to the ground state, then the emitted photon will be falling in the Lyman series, and this light cannot be seen. This is actually this radiation which is emitted here fall in the Lyman series. Actually, they are ultraviolet region. They fall in the ultraviolet region. The wavelengths are not visible by naked eyes because they will be in the ultraviolet range. Okay, so this is about Lyman series. Then we can actually go for excuse me. So here look, one important thing. Sometime they will ask you the Lyman series or the lines in the Lyman series or wavelength or frequency in the Lyman series falls in the ultraviolet, violet, visible, infrared, red, which region of the spectrum. So you have to say ultraviolet region. We cannot see Lyman series in naked eyes. Few more points you have to see here. They will say sometime the maximum wavelength in the Lyman series. So when you get maximum wavelength, that means if the energy difference is very less because they are reciprocal to each other. If you want to get maximum wavelength, your energy difference has to be less. So in case of maximum wavelength, see the wavelength will be 1 by 1 square minus 1 by 2 square. So you get r into 1 minus 1 by 4, that is 3 by 4 into r. This is the actually maximum wavelength. Then what will be the minimum wavelength? Minimum wavelength, in case of minimum wavelength, your this n n initial has to be infinity. This will give you minimum wavelength of this Lyman series. Not only, okay, so you look here. So the minimum wavelength and maximum wavelength, sometimes they will ask you to find out in terms of Rydberg constant what is maximum wavelength in the Lyman series, and what is the minimum wavelength in the Lyman series. Minimum wavelength will be r 1 minus 0, so 1 minus infinity, so this will be 0, so it will be in fact r. This is the minimum wavelength. Okay, so oh sorry, this is 1 over lambda minimum. So if you just take a reciprocal, so lambda minimum will be 1 over r. So this will be minimum wavelength of the Lyman series. Maximum wavelength will be 4r by 3. 4 by 3r. I'm sorry, this will be 3r down. Okay, this will be the maximum wavelength. Okay, I hope you are getting the points. Okay, so similarly, I'll go to the Balmer series. So in case of Balmer series, see this 1 by lambda is equal to this. So this is now the final state is n is equal to 2 square, and this initial state can start from anywhere starting from 3. Okay, if this is n is equal to 1, n is equal to 2, so Balmer series you start getting from n is equal to 3. If some electron make a transition from 3, you will get the maximum wavelength. You get minimum wavelength from infinity again, so n is equal to 4. So here n initial can be 3, 4, 5, 6, etc. Okay, this is actually Balmer series, and this is the only spectral series of hydrogen atom which falls in the visible range. So this is the only spectral series which can be seen in naked eyes. Okay, otherwise other things you have to see through spectrometer. Okay, so now what is, so it was Balmer, then Lyman series. I'll show you the figure itself so that you can understand from here. See, this is the Balmer when this is n is equal to 2, n is equal to 2 level. You can see this is the Balmer level, n is equal to 2 is the final state, and starting from n is equal to 3, n is equal to 4, n is equal to 5, etc. Okay, then it is actually in the visible range. Frequency or wavelength in the visible range. This was at ultraviolet range. Okay, ultraviolet range. And then Passon series actually the final state. See, I'll write 1 by lambda is equal to r 1 over. See, this will be 3, and this initial state can be an initial starting from 4 to anything. Okay, so look here, n is equal to 4, starting from n is equal to 4. This is the n is equal to 3 state. This is n is equal to 3 state. So initial like final state will be n is equal to 3, and initial state can be starting from 4, 5, 6, 7, like that it can go. So you will get a series of lines in the infrared region. So this Passon series, bracket series, and there is a Pfund series. So all three are infrared region, IR region. Infrared region. They fall in the infrared region. So there will be various numerical problems depending on this spectral series, like from what transition is giving Balmer series, and which transition gives Lyman series, the maximum wavelength of the Balmer series equal to minimum wavelength of the Lyman series, etc. It will be, and yeah. So these are actually the brief idea about various spectral series. will take up, I'll actually take up one class depending on the numerical problems which may come in various exams, so that day you will understand how we can use this knowledge to solve numerical problems. Now I'll finish this class with this just one simple concept, that is excitation potential. So we have seen that we have various energy levels. So suppose this is n is equal to 1, this is n is equal to 2, and then this is n is equal to 3, like that it goes, and you get finally a continuum state, okay, where there is no discrete energy level. These energy levels are continuous here. Okay, this is called ionized state. Ionized state, what do you mean by ionized state? We had somewhat understood. So look, I have an electron, okay, in some energy level, but when we take this electron to infinity, that means we are completely isolating this particular electron from this nucleus or from this atom, then the atom is called ionized, okay, and it will actually gain one positive charge, okay. So we say this is ionized. Hydrogen atom is ionized when we take the electron out, completely detached from the, or completely isolated, okay. We say it is infinity, you are taking it to infinity. When an electron is taken from particular atom to infinity, then the atom is called ionized, because no longer it will be neutral, one positive, so it will be positively charged then, okay, ionized. That's why it is called ionized atom. So for ionized, see, look here, one thing you have to understand, see, just like that electron cannot go infinity from this atom, because this nucleus is always attracting it. That's why you have, see, various bound state energy, like various energies. So this particular label also has certain energy. So to take the electron or electron from particular orbit to in enough amount of energy to knock it out from the atom completely, okay. So look, what is the energy you need to provide? Suppose, I'll clean this. Suppose I have an atom, sorry, I have an electron in the ground state, n is equal to 1, where the energy is actually minus 13.6 electron volt. I am just suppose this is continuum level, I am just ionizing it to this level, okay. So I'm just ionizing it, so this level has actually energy 0, so this is called E infinity. So what is the difference in energy? So the difference in energy will be 13.6 electron volt. So this much energy you need to provide to electron such that it can be excited to, like it can be knocked out completely from the influence of the nucleus, okay. So this is called excitation. And see, we need, sorry, this is called ionization, and we can ionize an electron from various states. We can ionize from ground state, we can ionize from first excited state, second excited state, etc. So in case of this incident, when we have an electron in the ground state and we are we are ionizing the atom from its ground state, then how much energy you have to provide? That is minus 13.6 electron volt, okay. So how you do this minus 13.6 electron volt? How you do that? Suppose I apply certain potential. To the electron. See, when I apply certain potential V to an electron which is at rest at this particular portion, and this region has potential V. So when the electron is accelerated in this region, electron gain a kinetic energy that is called 1 electron volt. If this is 1 volt, then it actually gains 1 electron volt energy. That means ionization potential is that potential, that minimum potential which is required to knock an electron completely out of the atom. That particular potential is called. So excitation potential is that potential. Okay, so it is that accelerating potential which gives a bombarding electron sufficient energy to excite the target atom by raising one of its, okay, this is exciting potential. So exciting potential means you are just exciting from one level to another level, that is called exciting potential. And ionization potential is that potential which gives enough energy to the electron to knock out completely from the atom. Okay, so that is called. So in this case, you have to give 13.6 volt potential to this particular atom. Okay, so that the electron will be knocked out completely from the atom and it will be ionized. So the energy which is required to supply an electron to be completely knocked out, that is called ionization energy, and the corresponding potential is called ionization potential. And if you want to excite from one level to another level, then the energy is called excitation energy, and the corresponding potential is called excitation potential. Okay, suppose I just want to excite an electron. Suppose this is the 13.6 electron volt minus, and this n is equal to 2. Suppose this is n is equal to 1, so this has energy minus 3.4 electron volt. Now you want to just excite an electron from here to here, so you have to provide this much of energy. So how much potential you should give? Excitation potential in this case 10.2 volt excitation potential you should provide. Okay, this is the minimum excitation potential. This is the minimum potential you require to excite an electron from ground state to first excited state. Now similarly, if you want to just knock out completely, so that is ionization potential energy, that we know potential energy is 13.6 you need, and corresponding potential is 13.6 volt, which you require to provide to that particular electron in the ground state to be completely knocked out from the influence of the nucleus. So these are called excitation potential and ionization potential. So next day we'll take up various examples depending on spectral series, ionization potential, excitation potential, and various other things related to atomic energy levels and an energy spectra. So I'll stop it here for today. We'll meet again on Sunday. So Deepa, if you have any question, quickly you can ask, or maybe anytime you can ask any other classes also if you have any doubt. Okay, if you don't have any doubt, we'll stop it here for today. So bye for today. We'll meet again on Sunday.